This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 05. Pump sizing with the extended energy equation. Very high yield. This lesson stitches together topics 02, 03, and 04, Bernoulli, Darcy-Weisbach friction, and minor losses to size a real pump between two reservoirs. Bernoulli assumes no energy input and no friction. Both break the moment a real pump is in the line. The extended energy equation keeps every Bernoulli term and adds 2, H sub P for the head the pump adds, and H sub L for the head loss to friction and fittings. This is the payoff for topics 02, 03, and 04. Continuity, Darcy-Weisbach, and minor losses all feed the pump sizing workflow. The extended energy equation, station 1 to station 2. Each side carries pressure, velocity, and elevation head. The left adds H sub P, the pump head. The right adds H sub L, the total head loss. Every term as units of length. When both stations are open surfaces with negligible velocity, 4 of the 6 head terms vanish, and it collapses to pump head equals elevation rise plus head loss. Recognize the pattern. The canonical stem is water pumped from one reservoir to another, with a stated elevation difference, and either a head loss or enough pipe data to compute one. Run the checklist. Steady, incompressible, along a streamline. No work, no friction. A pump fails the no work check immediately, so go straight to the extended energy equation. And before any algebra, draw the control volume. Both reservoirs, both stations, the pump, one common datum. The variable table is the densest in the course. 15 rows, givens and computed values. 7 are given by the stem. Density, flow, diameter, length, roughness, elevation rise, and pump efficiency. The other 8 are computed in sequence. Velocity, Reynolds, relative roughness, friction factor, Darcy-Weisbach head loss, minor losses, then pump head, and finally shaft power. Fill the table, and the answer falls out. Pump shaft power. In SI, it equals density times gravitational acceleration times flow times pump head over pump efficiency. In IP, the equivalent uses the constant 3960. Brake horsepower equals Q in GPM times H in feet times specific gravity over 3960 times eta. Water horsepower is the ideal with eta equal to 1. Brake horsepower is what the motor must actually deliver. NPSH Cameo, slide 1 of 2. NPSH available is the margin of absolute pressure above vapor pressure at the pump inlet, expressed as head. NPSH required is the curve the manufacturer publishes. The cavitation rule, available must stay above required. If it doesn't, vapor bubbles form and collapse violently on the impeller. Erosion, noise, vibration, eventually a destroyed pump. NPSH is not in Section 3 of the Handbook. Cite a fluids text such as Sengel or White. NPSH Cameo, slide 2 of 2. The formula, NPSH available equals atmospheric minus vapor pressure over specific weight, minus suction lift, suction line friction, and inlet velocity head. Worked quickly, the example lands on 4.5 meters. If the manufacturer's required NPSH at the operating flow exceeds that, the pump cavitates. The fix, lower the pump, shorten the suction line, or add a booster. Worked, exam-style problem. Water flows at 0.05 of a cubic meter per second through 120 meters of commercial steel pipe. 10 centimeters diameter, roughness 46 microns. The pump lifts at 20 meters between 2 open reservoirs. Sum of minor loss K factors is 8. Pump efficiency is 0.75. Find the required pump head and the shaft power, filling the table top down. Velocity from continuity. Area is pi times d squared over 4. Velocity is q divided by a, about 6.4. Reynolds number comes out to 6.4 times 10 to the 5th, deeply turbulent. Relative roughness epsilon over d is 4.6 times 10 to the minus 4. 3 rows down, 10 to go. Read the Moody chart. At this Reynolds and relative roughness, friction factor is about 0.0175. Darcy Weisbach gives an H sub F of about 43 meters. Sum the minor losses, K times the velocity head, about 16.5. Total head loss, H sub L, is roughly 60 meters. Friction dominates because the length over diameter ratio is 1200. The extended energy equation. Both pressure heads cancel because the surfaces are open. Both velocity heads cancel because the surfaces are large. No turbine. What remains is pump head equals elevation rise plus total head loss, about 80 meters of water. Friction dominates static lift 3-to-1 here. Sizing to elevation alone would deadhead the pump. Final answer. Shaft power equals density times gravitational acceleration times flow times pump head over efficiency. About 52.3 kilowatt, roughly 70 horsepower. The unit chain confirms watts. The variable table is now full. In practice, the motor would be selected one standard size above this, with a 15% service factor, putting the nameplate at 75 horsepower. Cylinder force cameo, adjacent to pump machinery. 3 relations to remember. Piston force is pressure times piston area. Piston velocity is flow divided by piston area. And power developed equals force times velocity, which simplifies to pressure times flow. For a double-acting cylinder, subtract the rod area contribution on the return stroke. A full cylinder design walkthrough is a future supplemental deck. 5 errors to avoid. 1. Mixing datums. Both elevations must reference the same horizontal line. 2. Plugging PSI into the energy equation without converting to PSF, off by a factor of 144. 3. Stopping at feet of water for a non-water fluid. Divide by specific gravity. 4. Calling water horsepower brake horsepower. Divide by eta for the shaft power the motor delivers. 5. Skipping the NPSH check on any pump with positive suction lift. Cavitation destroys the impeller. Take 5 things into the exam. The extended energy equation. The open surface collapse to elevation rise plus head loss. The pump power formula. The centrifugal characteristic curves, and the NPSH check on every suction lift pump. Onward to topic 06, pump curves, system curves, and affinity laws, where we find where the pump actually operates, not just what head it must deliver.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.